You know when you double-click an icon on your computer? Of course you do. A window pops up, a program starts running, but have you ever stopped to wonder what really happens in that split second? Today, we're going to pull back the curtain on that whole process.
Yeah, I think we've all been there, right? Staring at a screen, completely swamped by a sea of technical jargon. But honestly, the cool thing is the ideas behind how our programs actually run, they're not as scary as they look. We're going to break it all down together. I mean, think about it. It feels totally instant. It's something we do dozens of times a day and just take for granted. But in that tiny fraction of a second, there's a kind of magic happening where a simple file on your disk becomes a living, breathing process in your computer's memory. So, what exactly is going on in there?
Well, it all starts with the executable file itself, and the best way to think about this file is as a detailed blueprint, a complete set of instructions that the operating system uses to build and run the program.
Now, just like in the real world, not all blueprints follow the same format. If you're on Windows, you're using a format called PE, or Portable Executable. But for this explainer, we're going to focus on the format that's super common on Linux and other Unix-like systems, ELF. It stands for Executable and Linkable Format.
So what exactly is this ELF thing? Well, it's the standard file that a compiler spits out after it's done chewing on all the source code a programmer wrote. It's the crucial bridge between the ideas a human can write and the instructions a machine can actually execute. So let's lock in this analogy, okay? If the ELF file is the architect's blueprint, then your operating system is the construction crew, and the running program that you actually get to use, that's the finished, functional building. All right, so let's peek inside this blueprint. From a programmer's or a compiler's point of view, it's all organized into these logical chunks called sections. You can think of each one as holding a different type of material for the project. First up, you've got the .text section, and really this is the most important part. It's got the actual instructions, the raw machine code that the CPU is going to run. So if we had a simple program that prints out a lucky number, the literal step-by-step commands for doing that would be stored right here. This is the how-to part of the blueprint. Next up is the .row data section. Think of this as the supply list for stuff that's pre-made and can't be changed on the construction site, like a prefabricated window. In our little lucky number program, the actual text, my lucky number is %d/n, is read-only data. The program needs to be able to read it to show it to you, but it should never ever be able to change it. And that brings us to the data section. This holds the materials that come with a starting value but can be modified later. Kind of like a bucket of paint that starts as one color but you can mix stuff into. If our program has a variable like int lucky number equals 7, it starts out as 7, but the program is totally allowed to change it later. That variable lives right here in the data section.
Okay, but here's where it gets really interesting. Programmers and compilers think in sections, right? But the construction crew, the operating system's loader, it looks at the blueprint from a totally different perspective. It's only focused on how to actually build the thing in memory. The loader thinks in segments. So what's the difference? Well, it's all about perspective. Sections are for logically organizing the file on your disk. Segments are the loader's actual instructions for how to map all that stuff into the computer's memory so it can run. One is for storage, the other is for action. And this is absolutely crucial. Each segment comes with a set of really strict rules, or permissions. A segment can be marked as read, write, or execute. It's like the blueprint saying, okay, this area is just for looking at, this area is for storage, and this area has live wiring and is for execution only. So this slide just lays out that whole construction process perfectly. The loader basically has a 4-step job. First, it scans the blueprint to find the segments. Second, it stakes out a plot of land for the program in virtual memory. Third, it copies all the materials from the file into that memory space. And finally, and this is super important, it puts up the signs setting the correct read, write, or execute permissions for each part. And here's a perfect example of why this stuff is just so cool. Most programmers are taught that their code starts running in a function called main function. But that's not actually true. The real first function that gets called is a much lower level thing called _start. It's this little secret hidden deep inside the blueprint. And just like David Vernett says, this is the reward of systems engineering. You get to see how things really work. So we've gone pretty deep into this digital blueprint. But you might be asking, why? Why does any of this actually matter in the real world?
Well, it matters a ton. First off, security. Those read, write, execute permissions we talked about, that's a fundamental security feature. By making sure a data segment can't be executed, the OS stops a whole category of attacks dead in their tracks. Second, performance. This clear organization lets the OS manage memory way more efficiently. And finally, if you work in tech, this deeper understanding is what separates a good developer from a truly great one. So there you have it. That's the complete journey. From a static, lifeless bunch of bytes just sitting on your hard drive to a dynamic, running process actually doing work in memory. It's a pretty beautiful transformation, all guided every single step of the way by a well-drawn blueprint. We've seen how these executable files are the invisible blueprints for every single program we run. And it kind of makes you wonder, doesn't it? What other invisible blueprints, what other protocols and formats are out there quietly structuring the rest of our digital lives? Something to think about. Thanks for tuning in.